Welcome to SanfordFlipMath. This is AP Calculus. We are working through the Finney, Demana, Kennedy book. As you are aware, we are about halfway through Chapter 6. We're in Section 6.3, which is dealing with integration by parts. Talked about just doing antiderivatives in Section 1. In Section 2, we talked about integration by substitution. And the idea there is when you have a function inside of a function and its derivative is present, then it probably came from the chain rule, and then so you do some substitution based on the inside function, and then you can do the antiderivative much more easily. Well, the integration by parts again is based on a product similar to the U substitution situations, but the difference is that we don't have a factor that comes from the derivative of the inside. It's just a factor times a factor. Okay, and so like in this equation, this function, this antiderivative, this integral, indefinite integral that you see here, 3x did not come from the derivative of the inside of cosine, because that's just cosine x. Cosine x did not come from the derivative of the inside of 3x, which I don't really see what the inside is. So the idea here is we just have a product, and it's not from the chain rule. So my inclination is probably integration by parts. Okay, now remember we have a little process here to decide which function, which piece of this gets to be u. Okay, so this whole thing in order is how we choose u. So I'm looking at this, I see a 3x and I see a cosine x, and I say to myself, do I see a log function in there? Nope. Do I see an inverse trig function? Nope. Do I see a polynomial function? Yep. So 3x is a polynomial function. So since that's the first one I came to, I'm going to have that be my u. Okay, so I'm not going to get to the exponential or trig in this list. This is going to be, this whole thing then becomes dv. Okay, now again, it doesn't have to be in order left to right, u and then v. It's just understand that this is, you choose it based on the whole LIPET thing. Okay, all right, so this example is a pretty straightforward example, like what we did in the last video, and it's going to get a little more interesting. Okay, so I'm going to take this u, and I need to find out what du is. So du dx is just going to be 3. So d is 3 dx. Okay, now this guy is the dv, so we're following this pattern. Okay, so we have the u, and now we have dv. And it is cosine x dx. So that means doing the antiderivative of both sides, v equals sine of x. And there could be a plus c there, but we'll deal with that later. Okay. All right, so again, not negative sine, because the derivative of sine to get me back to dv, derivative of sine is just cosine. Okay, and I know that can get a little confusing. All right, so we're following the pattern, u times v. So 3x times sine x minus the antiderivative of, well, now we're going to do v du, like voodoo is the way I remember it. So v is sine x, du is 3 dx. Okay, I'm just looking at my list over here on the right. Okay, I'm going to rewrite this one more time, and then we'll do another antiderivative. Okay, so sine x minus, I'm going to bring that 3 out front because it's not doing jack diddly do in there, and I can take a constant out. Okay, and so at this point, now I can do this last antiderivative because now it's fairly straightforward. Okay, so this becomes minus 3 times the antiderivative of sine is negative cosine. So I'm going to put that as a plus, and I need a plus c on the end, and we can wrap that sucker to go. It is done. Okay. So fairly straightforward. I will tell you that sometimes it gets a little crazy. Okay, so I want to go back and remind you of one that we did in the last video, and I believe it is not that one. Next one, this one. And I'm not redoing it. I just want to point it out to you because, well, I am going to redo it, but I'm going to do a slightly different technique. Okay, so just a quick little recap here. When we were doing this, the x squared was the u, and we went through the whole process. I'm not going to do the whole thing. And so x squared was u, and then we did a derivative of that to do the du part of it, and here it is. and then it was still there. So we had to do it again. So we had to do parts twice, and it was kind of a big pain in the, yeah. Okay. So what I want to do is show you kind of a simpler approach. It's the same thing, but the parts part gets a little bit masked in this. So here's that same problem again, and we're going to do what's called tabular method. Well, tabular just means with a table. And the idea here is we ended up doing u times v minus v du, but we had to then this was a whole new one, and we had to do it again. Okay, so, and we used the new du as our new u in the second one. All right, how about I just do it? Okay, so the way this is going to look is we're going to have two columns in our table. This is going to be u and the derivatives of u. This side is going to be dv and the antiderivatives. Okay, so you're doing derivatives down the u column, antiderivatives down the dv column. Okay, because that you want to get from dv to v. Okay. So we would still go through the whole LIPET thing. And so is there a log? No. Is there an inverse trig? No. Is there a oh yeah, there's a polynomial. Okay, so this sucker is u, and this thing is going to be my dv. Okay, so just kind of starting my little list here. Okay, so u is x squared, and then dv is cosine of x over 2. Okay, now, so what I'm going to do with the u column is I'm going to go down this list and I'm going to do derivatives until I get to 0. So derivative of x squared is 2x. The derivative of 2x is 2. The derivative of 2 is 0. Okay, antiderivative. Okay, so we're on this side now. Antiderivative of cosine is sine. Now, the only problem is that there's a magical 2 that comes there. Well, you know it's not magical. And if I just do a quick little u equals x over 2, then du is 1/2 x. And that 1/2 is supposed to happen somewhere, but it canceled out, and it canceled out with a 2. And there's a lot of hoopla that goes on here. Suffice it to say, it's kind of like when we do, if we were doing the antiderivative of, well, let's pretend for a second we were doing antiderivative of 2x. Remember that that comes out to be sine of x over 2, I'm sorry, sine of 2x over 2. And again, this comes from this. You know, it was sine of kx over k when this was k. And we learned that rule, and the idea here is the k is really 1/2. So over 1/2 makes it multiply by 2. I don't know, that's probably confusing, and you can kind of play around with it and straighten it out. Okay, I need a row for every row in the left column. So that means I need to do another antiderivative here. So the antiderivative of sine is negative cosine, and it's x over 2. And because of that over 2, I'm going to multiply by 2 again. One more time. Antiderivative of cosine is just sine, x over 2. And again, the antiderivative of the x over 2 part, that over 2 is going to create another multiplication by 2. And this negative is not a new negative. This is that same negative from there. Okay? All right. The hard part's done. And I know this doesn't seem like it, but it is. Okay, so what happens is, remember the first part of the parts formula is uv. Well, this is u, and this is my first v, because this guy was dv. So what we're going to do is write x squared times 2 sine x over 2. And then what you do is you alternate signs. So this starts out whatever sign it was. Okay, so I'm going to label it positive. And then you go here on the negative, or on the diagonal, and this one's going to be minus because it's uv minus the integral of. Okay, so this one's going to be minus, and it's going to be 2x times negative 4 cosine x over 2. Sorry, too far. Okay, then we're going to do it again. Now again, these signs alternate. So this was plus, in other words, whatever sign it was. This was minus, meaning do the opposite sign. This will be plus, okay? And so do whatever sign it is. And I'm going to just do plus 2 times negative 8 sine. Yes, I could write that better, and I will. Okay, now the next term is going to be 0 times, so we don't care. Okay, so let me just clean this up a little bit. So this is going to be 2x squared. This will be minus a negative, so plus 8x. Yeah, I'll put parentheses there. I don't need them, but I will. And minus 16 sine x over 2. Okay. And that is that. So 2x squared plus 8x minus 16. Let me just pop back and let's do a little comparison. Two x squared minus 8x plus 16. Oh, I think I forgot my plus c. I think this is the first time. And I hate forgetting that, but I've done pretty well. Ah, plus c. All right. I was doing so well, too. I hope somebody was yelling at me. Mr. Sanford, you forgot your plus c. Thank you. All right, there it is. Okay, so tabular method, the whole point of tabular method is when you know that you're going to have to do u and then du and then the d of du and then the d of d of d of d. I don't know how many d's I had there, but the idea is you're going to have to repeatedly do it because you need that term to kind of go away. Okay? And so tabular is just kind of a sweet way to do this so that it goes away quicker. Okay? All right. Let's do another one. Same idea, same exact idea. Okay? All right, so again, the idea is, again, going through the LIPET thing, the u cubed is a polynomial. And then this is trig. Okay, so this will be dv. Okay? And the idea here is when I do the du, I would have 3x squared. When I do the du again, I have 6x. And it's going to take a few cycles for this thing to go away. Okay? So oftentimes the point of this is when you do the derivative part of the du, then the u's eventually go bye-bye. Okay? All right, so here we go. U and the du's. That's funny. dv, sorry, and the v's. In other words, antiderivatives. Okay? All right, so let's start with u. I mean, not like you and me, but yeah. Okay, so x cubed, 3x squared. Again, I'm doing derivative until I get down to 0. 6x, still not to 0. Derivative of 6x is 6. Derivative of 6 is 0. Nice. Okay, I knew I was going to get there. Cosine of 2x, and don't worry about the dx because we're going to be doing antiderivatives and we know it, and we're not writing all the notation here. Antiderivative of cosine is sine 2x, and it's going to be over 2. You can go through the u substitution here if you want, but it's going to just be so much easier if you just remember that. Antiderivative of sine is negative cosine, and I need to divide by 2 again. The antiderivative of negative cosine is negative sine, not because antiderivative of cosine is negative, but because this negative sign comes along. And divide by 2 again. Okay, just to clarify what's going on here. I need a row for every row all the way down to 0. Because what we do is we hit the diagonals. Okay, so the antiderivative of sine is negative cosine. And the negative of that negative goes back to positive. And then I need to, again, divide by 2 again. So over 16. Okay, can you imagine writing this out step by step and doing all the different steps? I mean, it works, but it would take a long time. All right, so this is my first term. This is u times v. U times v. Okay, so x cubed. Oh, I need to. Okay, here we go. X cubed sine 2x over 2, I believe it was. Yep. Okay. Next one. Okay, so remember that they alternate signs. So I'm going to do minus. So minus 3x squared times negative cosine 2x over 4. And the whole idea, they always alternate because the next one would have been minus again, and you would have had minus a quantity, and you'd have been distributed in the sign and whatever. You can play around with it and see it. Okay, so this time it's the same sign. 6x, and then times negative sine 2x over 8. And I'm bummed that I'm running out of room, but that's just how it is. Okay, again, we are alternating signs. Okay, so this is going to be minus 6 times cosine 2x over 16. And then the next term would have been 0. Okay, so I'm just going to clean this up a little bit. Okay, and I know I'm just kind of moving along here, but remember, you can pause any time. Okay, so all of this is going to be equal to 1/2 x cubed sine 2x. Next one's plus because it's minus a negative, and this bad boy is going to be 3/4 x squared cosine. Next one is going to be plus a negative, so minus. Now 6 over 8. I'm going to go ahead and reduce that because I don't feel like writing this 17 times. Do not, sorry, usually it's algebra issues. Do not take that 2 and that 8 and think, oh cool, I can reduce that. No, you can't. That 2 is not a 2. That 2 is part of the sine of 2x. All right, so where was I? Minus 3/4 x sine of 2x. Okay, last but not least. Now again, this is 6 over 16, which we're going to call 3/8. So minus 3/8 cosine 2x. Ha ha ha! Plus c. I was so excited it all fit on one row, and it almost did. Caught myself. I almost forgot that plus c. You know, you do all that work, and that plus c is easy to forget. So I understand the issue. You just have to remember. Okay. All right. So that's it for the tabular method. Tabular method. That is the idea. All right. There's one more ugly thing, and this is going to take some time, and it's not going to be pretty. Okay. So what we're going to do is, again, 2x, the derivative of 2x would be 2. E to the negative x has nothing to do with that. If this would have been e to the negative cosine of 2x, then maybe we'd be doing some u substitution here. But it's not, so we're not. And so the idea here is that it's going to be parts. Okay. So the goal is to find that derivative. Okay, and following the whole LIPET thing, I don't see any log stuff. Remember, e to the x is not log. E to the x is exponential. Okay, so log is out. There's no inverse trig. I don't see any polynomial. First thing I see is exponential. So this is exponential. The next thing is trig. So this is u, and the rest of this is dv. Now, here's the issue. When you do the derivative of u, you're going to get negative e to the x. When you do the derivative of that, you're going to get negative e to the negative x, I think another negative, so back to positive. And then you do the derivative. So anyway, the idea is it's going to just be, it's never going to go away. Like with x to the cubed, I know if I do the derivative of x, when I do the derivative of x cubed, it's x squared and works down to x, and then eventually those derivatives go away. You know, like when we were looking at this tabular form, you know, the derivatives end up going away here. Okay, whereas with this, that's not going to work. Okay, so, and sine, when I do the antiderivative of sine, it becomes negative cosine, and I do the antiderivative of that, that's going to be sine. So that's not going to go away. So the hope is that a miracle happens. So let's go looking for our miracle. Okay, so du is going to be, so again, u is e to the negative x, so du is negative e to the negative x. Now why is that negative? Chain rule. So du, negative e to the negative x dx. Okay? dv is sine of 2x. So v is going to be negative cosine of 2x over 2. Okay. All right, so that's it for that, and let's just see what happens. Okay, so uv times v, well, this is going to be negative, I'm going to put it out there, cosine 2x over 2 minus the antiderivative of v. Well, I'm going to go ahead and pull the negative and the over 2 out in front. So this is going to be 1/2 cosine 2x times du, negative e to the negative x dx. Well, that's just not even fun, is it? All right, not a big fan of this. I'm going to go ahead and rewrite this. And I mean, you probably can sense that I don't even like this stuff. So sorry, but it is part of what we need to do here. Okay, I'm going to pull that negative out in front. So this is negative 1/2 antiderivative of e to the negative x cosine 2x dx. Well, you're probably noticing that this integral, this guy, is not really any better than this one. So did that even help us? Well, let's do it one more time, and then the miracle will happen. Okay? Okay, so I have to bring along all of this crud. Okay, and then what we're going to do, we're going to focus in on this integral, which is, again, pretty much the same kind of setup that we just had. Okay, so off to the side here, I'm going to do my u and dv stuff. And again, u is going to be the e to the negative x, so du equals negative e to the negative x dx. Similarly, yep, I dropped it. Dv is cosine 2x dx, so v is going to be sine 2x over 2. Okay. All right, so all of this, we're going to do parts again, but it's all got to be kind of bracketed together. We've got to hold this sucker together, and all of this will be equal to the integral we're trying to find. Okay, so here we go. So uv, so e to the negative x times v, sine 2x over 2 minus the antiderivative of v du. Du is negative e to the negative x dx. All right, doesn't look very miraculous right now. Okay, so what I need to do is I need to clean this up. I have a lot of distributing to do, and then we'll let the miracle happen. Okay. So this is, again, negative. I'm just recopying now. Okay, now I'm distributing. So, like, this video is going to go a little long. This is the last example I'm doing, but I got to get to the end of it. Okay. So negative 1/2 times all of this stuff is going to be a negative 1/4 negative 1/2 times all of this, and again, I got a lot of stuff going on. I have a negative and a 2 and all of that. So this is all going to be negative times a negative times a negative, negative 1/4 e to the negative x. Oh, sorry, I need antiderivative. E to the negative x sine 2x dx. All right, well, you see it? Do you see it? Yeah, probably not. All right, so let me remind you of the original problem we were trying to do. E to the negative x sine 2x. All of this is supposedly equal to e to the negative x sine 2x. I mean, this is what we wanted this all to be equal to, right? We're trying to find this. Okay, this is our goal. Now, what I need you to see is that this thing is the same as this thing. And they're on opposite signs of an equal sign. Okay. Okay. Let me just rewrite this again so you can see it all in one shot. Okay. All right. Here it is. It's all rewritten again, and so it's all the same thing. And I put the original problem on the left, and it's all equal to all of that stuff. Okay. So what I need you to see is think of this integral, the thing that we want to know. Think of it like a giant variable. So I don't know. Let's pick a big q. Great. I don't know. I just need something. And this is a negative 1/4 q. And I'm just making up q. It doesn't have to be that. But the idea then is if I think of this like solving an equation for a big ugly variable, I can add the 1/4 q to each side. And then when I do that, on the left side, this is 4/4 plus 1/4 is 5/4. We're almost done. I can feel it. I'm excited. Equals all that stuff. Okay, and then this part just added up to 0. Isn't that magical? Okay, and so remember the goal, again, is to find this. Well, if the goal is to find this, q, or whatever we're calling it, then I just need to get rid of this 5/4. So I'm going to multiply by 4/5 on each side, and I'm done. Okay, so let me just rewrite. Okay, so as I'm distributing 4/5 here, I have some fractions to reduce. So like the 2 and that, so this becomes negative 2/5. Okay, and just kind of stare at it for a bit. Here the 4's divide out, leaving just a minus 1/5. And that is it. Oh, yep, I caught myself. Whew, so far I've been doing good, doing well, pardon me, plus c. Now if there were limits to integration on this, we would have to go and substitute and all that kind of stuff, okay? Okay, probably worth noting that you could have left the 4/5 on the outside and even factored out a negative e to the negative x or something like that, but this works. Okay. All right. Well, that's as bad as it gets as far as specifically integration by parts problems. They don't get any worse than that, and we're done with this. Thank you for hanging in, and I know this was ugly, but you need to know how to handle this. This will come up in the homework, and it's very likely to happen on a test. I would not have more than one problem like this on a test, but it is possible to have this happen. Okay. Thanks for hanging in. Again, SanfordFlipMath. We are out of here. Bye.